Hello there, and welcome. If you're here right now, maybe you're looking for something to help you relax. Maybe the day has been long, and your mind needs a place to rest. Maybe you want to learn something beautiful while you drift away into sleep. Whatever brought you here tonight, I'm glad you're here. Let your shoulders drop. Let your breathing slow down. There's nowhere else you need to be right now. Before we begin, if you enjoy falling asleep to stories about the universe, go ahead and tap that like button. And if you want more videos like this, consider subscribing. But no pressure. You're here to relax, not to work. The Big Bang is the name scientists give to the beginning of our physical universe. But it wasn't really a bang at all. There was no sound, because sound needs air to travel through, and air didn't exist yet. There was no explosion in space, because space itself was being born. It's hard to imagine, isn't it? A moment when there was no space, no time, no matter, no light, and then, suddenly, everything began. So close your eyes if you want to, or keep them open and stare at the ceiling. Get comfortable. Pull your blanket a little closer. And let's begin our journey back to the very beginning, to the moment when everything you know came into being. Let's drift together through time, back to when the universe was young and hot and simple, and watch as it slowly becomes the complex, beautiful cosmos we call home. Fact 1. The Big Bang happened approximately 13.8 billion years ago. That's the current age of our universe, measured with remarkable precision by scientists using multiple methods. They figured this out by measuring how fast galaxies are moving away from us and working backwards, like rewinding a movie. They also studied the cosmic microwave background, that ancient light from the early universe, and analysed its patterns to determine how long it has been travelling. When you look up at the night sky, you're looking at a universe that has been growing and changing for almost 14 billion years. Every star, every planet, every atom in your body is part of that long, incredible story. It's a story that stretches back through time so far that it makes human history look like the blink of an eye. All of recorded civilization, every empire that ever rose and fell, every person who ever lived exists in just the tiniest sliver at the end of that vast timeline. Fact 2. Before the Big Bang, there was no before in our sense of time. This sounds strange, maybe even impossible to grasp, but time itself started with the Big Bang. You can't ask what happened before it, because before didn't exist yet. Time is not something that sits outside the universe like a container. It's something that belongs to our universe. It's woven into the fabric of space itself, part of what scientists call space-time. So when the universe began, time began with it. There was no clock ticking in the darkness, waiting for everything to start. There was no empty void sitting there for eternity, until suddenly the universe appeared. The first tick of the clock was the Big Bang itself. This means that questions about what came before become difficult to answer with physics alone. Cause and effect as we understand them require time to exist. It's one of those ideas that makes your brain twist a little, and that's okay. Some truths about the universe are bigger than our everyday experience can easily hold. Fact 3. The Big Bang was not an explosion that happened somewhere in space. It was the expansion of space itself. This is one of the most misunderstood things about the Big Bang, and it's worth taking a moment to really think about it. Imagine a balloon with dots drawn on it. When you blow up the balloon, the dots move away from each other, but none of them is at the centre. They're all moving because the balloon itself, the surface they sit on, is growing. That's what happened with our universe. Space itself stretched out in every direction at once. There was no centre point, no edge where the expansion started. Every point in the universe was part of the beginning. If you could have stood anywhere in the early universe and looked around, you would have seen everything expanding away from you, making it look like you were at the centre. But every other point would have looked the same way. The universe doesn't have a centre, or if it does, every point is equally the centre. It's expanding everywhere at once, and it has been since the very first moment. Fact 4. In the very first moment after the Big Bang, the universe was incredibly hot. We're talking about temperatures around 10 billion degrees Celsius or more. That's hotter than the centre of any star you can see in the sky. That's hotter than anything we can create on Earth, even in our most powerful particle accelerators. Everything was pure energy, blazing with a heat we can barely imagine. There were no atoms yet, no molecules. Nothing solid or even anything you could call matter in the normal sense. Just energy, packed into a space smaller than you can picture, burning with impossible fire. The universe was so hot that the fundamental forces of nature, the rules that govern how particles interact, might have been unified into a single force. Gravity, electromagnetism, the strong nuclear force and the weak nuclear force, all the things that shape reality, might have been one thing in that first instant. Then, as the universe expanded and cooled, they split apart into the separate forces we know today. Fact 5. The universe started out smaller than a single atom. In fact, scientists think it might have started as a point with no size at all, something called a singularity. All the energy, all the matter, everything that would one day become galaxies and stars and planets and you, was compressed into something impossibly tiny. The density was infinite, meaning infinite mass packed into zero volume. Our mathematics breaks down when we try to describe this moment. The equations that usually tell us how the universe works give us answers that don't make sense, numbers that are infinite or undefined. Then it began to grow. It grew faster than anything has ever grown, stretching from smaller than an atom to larger than a galaxy in just a fraction of a second. This wasn't just things moving apart through space. This was space itself expanding, carrying everything with it. The universe went from unimaginably small to incomprehensibly large in less time than it takes light to cross a single atom. Fact 6. This incredibly fast growth at the beginning is called cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded faster than the speed of light. Yes, faster than light, and by a huge amount. That sounds impossible, because we always hear that nothing can go faster than light. Einstein's theory of relativity tells us that nothing can move through space faster than light speed. But that rule applies to things moving through space. Space itself can expand as fast as the laws of physics allow. There's no speed limit on the expansion of space itself. And in those first moments, it expanded at a speed that makes light look like it's standing still. The universe might have doubled in size 60 times or more during inflation. Each doubling happened almost instantly. By the time inflation ended, the universe had grown by a factor bigger than we can easily comprehend, something like 10 to the power of 26. That's a 1 followed by 26 zeros. Imagine a grain of sand expanding to become larger than the observable universe. That's the kind of growth we're talking about. Fact 7. Through the Big Bang, all the matter in the universe came into being. Every atom in your body, every particle of air you breathe, every drop of water in the ocean, every grain of sand on every beach, every star in every galaxy, it all came from that first moment. Matter and energy are two forms of the same thing, connected by Einstein's famous equation, E equals mc squared. In the beginning there was only energy, pure and formless, but as the universe cooled down, that energy transformed into particles. First came quarks and electrons, the basic building blocks of matter. Those particles became atoms when the universe cooled enough for them to stick together. Those atoms became gas clouds. Those gas clouds became stars. Those stars created heavier elements, and eventually on at least one small planet orbiting an ordinary star, those elements came together in just the right way to create life. You are made of matter from that first moment. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, it all traces back to that initial creation. Fact 8. For the first 380,000 years after the Big Bang, the universe was completely dark. Well, not exactly dark, and this is an interesting point to think about. It was full of light, full of energy, but the light couldn't travel. The universe was so hot and so dense that light kept bouncing off particles trapped like a bird in a cage. Photons, the tiny packets of energy that make up light, couldn't move freely through space. They would travel a tiny distance, smaller than the width of a human hair, and then hit an electron and bounce in a different direction. So even though energy was everywhere, even though the universe was glowing white hot, you wouldn't have been able to see anything if you were somehow there. It would have been like being inside a thick fog, except the fog was made of plasma, and it was billions of degrees hot. The universe was opaque, and it stayed that way for hundreds of thousands of years while space expanded and everything slowly cooled down. Fact 9. The universe was made of plasma in those early years. Plasma is what you get when matter is so hot that electrons break free from their atoms. It's like a soup of charged particles, all zipping around at incredible speeds. The entire universe was filled with this glowing, dense fog of plasma. You can see small amounts of plasma on Earth. Lightning is plasma. The inside of a fluorescent light bulb is plasma. The sun and all stars are made of plasma. But in the early universe, everything was plasma. There was nothing else. Stars couldn't form yet because the universe was too hot and too uniform. Planets were impossible for the same reason. There was just this hot, thick plasma, slowly cooling as space continued to expand and stretch and carry the heat away. The temperature was dropping, but it was still thousands of degrees, hotter than the surface of any planet, hotter than molten rock, hotter than any furnace, and it stayed that way for what would feel like a very long time if anyone had been there to experience it. Fact 10. 380,000 years after the Big Bang, something important happened. The universe had cooled down enough for electrons to stick to atomic nuclei. The temperature had dropped to about 3,000 degrees, cool enough for atoms to form and stay together. When that happened, light could finally travel freely through space. Scientists call this moment recombination, even though it's really the first time electrons and nuclei combined. It's when the universe became transparent. The fog cleared. Light could suddenly race across space without being stopped every fraction of an inch. That first free light went shooting out in all directions, travelling through the expanding universe. And here's the beautiful thing. That light is still travelling today. It has been journeying through space for over 13 billion years, and we can actually detect it and study it. It carries information about what the universe was like when it was just a baby, less than 1% of its current age. Fact 11. The light from that moment, from 380,000 years after the Big Bang, is still reaching us now. We call it the cosmic microwave background radiation, or CMB for short. It's like an echo of the beginning, a whisper from the early universe that has been travelling through space for over 13 billion years. Scientists can detect this ancient light with special telescopes designed to see microwave radiation. It comes from every direction in the sky, a gentle glow that fills the entire universe. No matter where you point your telescope, you see it. It's everywhere, surrounding us like an invisible ocean. The cosmic microwave background is the most distant thing we can observe. When we look at it, we're seeing light that has been travelling for almost the entire age of the universe. We're looking back through time to an era when the universe was young and simple and nothing like it is today. It's the oldest baby picture we have of the cosmos. Fact 12. The cosmic microwave background is the oldest light we can see. Before recombination, light couldn't travel, so we can't see anything from those earlier times, at least not with light. When you look at the cosmic microwave background, you're looking back in time, seeing the universe as it was when it was just a baby. This light has been stretched out by the expansion of the universe. It started as visible light, bright and hot, with a temperature of 3,000 degrees. If you could have been there to see it, the universe would have glowed with a warm orange-red colour, like heated metal in a forge. But as space expanded over billions of years, the light stretched too. The wavelengths got longer. What started as visible light shifted into infrared, then into microwaves. Now it's in the microwave part of the electromagnetic spectrum, the same kind of radiation used in microwave ovens, though much, much weaker. We can't see it with our eyes, but we can detect it with instruments, and when we do, we're touching the edge of the visible universe, seeing as far back in time as light will let us see. Fact 13. In the 1960s, two scientists named Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background. They were working at Bell Labs in New Jersey, trying to use a radio antenna for astronomy. They were studying radio waves from space, looking at the Milky Way galaxy. But they kept picking up strange noise, a constant hiss that came from every direction. At first, they thought it might be interference from New York City. Then they thought it might be a problem with their equipment. They even thought it might be pigeon droppings interfering with their antenna. Because pigeons had been nesting inside the equipment, they cleaned everything carefully. They removed the pigeons and cleaned away all the droppings. The noise didn't go away. They checked everything they could think of. Finally, they learned about a theory that predicted there should be leftover radiation from the Big Bang. Eventually, they realized they had found something incredible. They had detected the afterglow of the beginning itself, a signal that had been travelling through space for billions of years before finally reaching their antenna in New Jersey. They won the Nobel Prize for this discovery, which gave us one of the strongest pieces of evidence that the Big Bang really happened. Fact 14. The early universe was almost perfectly smooth, but not quite. There were tiny, tiny variations in temperature and density from one region to another. Some regions were just a little bit hotter or a little bit cooler than others. Some places had slightly more matter, and some had slightly less. These differences were incredibly small, less than 1 part in 100,000. If the average temperature was 3,000 degrees, the variations were only about 3/100ths of a degree. But they mattered more than you might think. Those tiny ripples were the seeds that would eventually grow into galaxies and clusters of galaxies. The places that were slightly denser had slightly more gravity. That extra gravity pulled in more matter from the surrounding space. As more matter gathered, the gravity got stronger, pulling in even more matter. Over millions and billions of years, those tiny differences grew into the large structures we see today. Without those small imperfections, the universe would have stayed smooth and empty forever. All the matter would have been spread out evenly, and nothing interesting would ever have formed. No stars, no galaxies, no planets. No life. Those tiny ripples allowed complexity to emerge. Fact 15. For hundreds of millions of years after recombination, the universe was dark again. This period is called the Cosmic Dark Ages, and it's one of the least understood eras in cosmic history. There were no stars yet to light up the darkness. The hydrogen gas that filled space was cold and neutral, just drifting in the void. The only light was the cosmic microwave background, but it was fading and cooling as it stretched across the expanding universe. It must have been a lonely time, if anyone had been there to see it. Just darkness and gas and gravity, slowly pulling things together. The matter was gathering in some places and emptying out of others, following the pattern set by those tiny initial ripples. Dense regions were getting denser. Empty regions were getting emptier, but it all happened in darkness. The universe was like a stage before the performance begins, with all the actors taking their places in the shadows, waiting for someone to turn on the lights, and slowly, over hundreds of millions of years, the first stars began to form and the lights came on. Fact 16. The first stars formed about 100 to 200 million years after the Big Bang. These were nothing like the stars we see today when we look up at the night sky. They were massive, much bigger than our sun, sometimes 100 times heavier or even more. They burned incredibly hot and bright, shining with a fierce blue-white light, and they didn't last long, maybe just a few million years before burning out. These ancient stars are called population 3 stars by astronomers, though none of them exist anymore. They all burned out billions of years ago, dying in spectacular explosions. But while they lived, they changed everything. They were the first sources of light in the universe since recombination. They ended the cosmic dark ages. They heated the gas around them and created bubbles of ionized hydrogen. And most importantly, they created new elements that had never existed before, elements that would be essential for planets and life. Fact 17. Those first stars created the first heavy elements through a process called nuclear fusion. When the universe began, it was made mostly of hydrogen and helium, the 2 lightest elements. Hydrogen is the simplest atom, just 1 proton and 1 electron. Helium has 2 protons, 2 neutrons, and 2 electrons. Together, these 2 elements made up about 99% of all matter. But inside the cores of stars, something remarkable happens. The heat and pressure are so intense that atoms can fuse together, combining their nuclei to make heavier elements. Hydrogen atoms combine to make helium, helium atoms combine to make carbon and oxygen. Bigger stars can create even heavier elements like neon, magnesium, silicon, and iron. The most massive stars can forge elements all the way up to iron in their cores. When those first stars died, they scattered these new elements into space, enriching the universe. The next generation of stars that formed included these heavier elements. And slowly, over billions of years and many generations of stars, the universe built up a supply of all the elements we know today. Fact 18. The death of the first stars was spectacular. When a massive star runs out of fuel, it can no longer produce the energy needed to push back against its own gravity. The core collapses in on itself in less than a second, and then the outer layers explode outward in what we call a supernova. These explosions are so bright they can briefly outshine an entire galaxy containing billions of stars. The first supernovas lit up the dark universe like fireworks going off in the night. They sent shockwaves through the gas clouds around them, compressing the gas and sometimes triggering the formation of new stars. And they sprinkled space with heavy elements, the building blocks for planets and eventually for life. Every supernova is a moment of both death and creation. A star dies, but in dying, it seeds the universe with the materials needed to build new worlds. The iron in your blood came from a supernova. The calcium in your bones came from a supernova. You carry the remnants of stellar explosions inside your body. Fact 19. Through the Big Bang, the lightest elements came into being, but not all the elements. It only made hydrogen, helium, and tiny amounts of lithium and beryllium. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every bit of iron in your blood, every atom of gold in any ring or necklace was made inside stars or in supernova explosions. You are literally made of stardust. This isn't just poetic language, it's scientific fact. The atoms that form you were forged in the hearts of dying stars billions of years ago. Those stars lived their lives, burned brightly, and then exploded, scattering their enriched material into space. That material became part of new clouds of gas. Those clouds collapsed to form new stars and planets. One of those planets was Earth, and billions of years after the supernovas that made your atoms, here you are, a living being made of star matter, able to look up at the sky and understand where you came from. In a very real sense, you are part of an incredible cosmic journey. Fact 20. About 3 minutes after the Big Bang, the universe had cooled enough for the first atomic nuclei to form. This process is called Big Bang nucleosynthesis, and it happened in a very brief window of time. Before 3 minutes, the universe was too hot. The particles smashed into each other so hard that they couldn't stick together. After about 20 minutes, the universe was too cool and too spread out. The density and temperature dropped below what was needed for fusion to happen. But in that window, between about 3 and 20 minutes after the beginning, nuclear fusion happened throughout the entire universe. Protons and neutrons, the particles that make up the centers of atoms, started sticking together. Most of them formed hydrogen nuclei, which is just a single proton. Some formed helium nuclei, which have 2 protons and 2 neutrons. Tiny amounts of lithium and beryllium also formed. This all happened in just a few minutes. After that, the universe was too cool for fusion to continue. So for a long time, hundreds of millions of years until the first stars formed, hydrogen and helium were all there was. Fact 21. The proportions of hydrogen and helium in the universe match almost perfectly with what the Big Bang theory predicts. This is one of the most compelling pieces of evidence that the theory is correct. About 75% of the normal matter in the universe is hydrogen. About 25% is helium. The rest is everything else, all the other elements combined, making up just a tiny fraction, around 1 or 2%. These numbers match the predictions from Big Bang nucleosynthesis calculations extremely well. Scientists can use the physics of nuclear reactions and the conditions in the early universe to predict exactly how much hydrogen and helium should have been created. When they do the math, they get the same numbers we see when we look at the universe today. This match between prediction and observation is one of the strongest pieces of evidence that the Big Bang really happened. It's hard to imagine any other explanation for why the universe has exactly the proportions of elements that the theory predicts. Fact 22. The universe is still expanding today. In fact, it's not just expanding, it's expanding faster and faster. The rate of expansion is accelerating. Scientists discovered this in the late 1990s, and it came as a huge surprise. They were measuring distant supernovas, using them as markers to track how the universe has grown over time. Supernovas are useful because the very brightest ones always have about the same actual brightness. So if you see one that looks dimmer, you know it's farther away. By measuring how dim they appear and how fast they're moving away from us, scientists can figure out how the expansion rate has changed over time. They expected to find that gravity was slowly pulling everything back together, slowing down the expansion. After all, every piece of matter in the universe pulls on every other piece through gravity. It seemed obvious that this would gradually slow the expansion. Instead, they found the opposite. The expansion is speeding up. Distant galaxies are moving away from us faster and faster as time goes on. Fact 23. We don't fully understand why the expansion is accelerating. Scientists call the mysterious force behind it dark energy. But that's really just a name for something we don't understand. It's like calling an unknown noise in your house, that weird sound. The name doesn't explain anything. Dark energy seems to make up about 68% of all the energy in the universe, which means it's the biggest single component of reality. It's pushing space apart, working against gravity. We can measure its effects by looking at distant supernovas and by studying the cosmic microwave background and the way galaxies are distributed through space. But we don't know what it is. We don't know where it comes from. We don't know if it's a new kind of energy field or a property of space itself or something else entirely. It's one of the biggest mysteries in science, and solving it might require new physics, new laws of nature that we haven't discovered yet. For now, all we can say is that something is making the universe expand faster and faster, and we call it dark energy, because we're in the dark about what it really is. Fact 24. Dark matter is another mystery that came from studying the Big Bang and the universe's history. When scientists look at how galaxies move and how they're distributed through space, the math doesn't work unless there's much more matter than we can see. Galaxies spin faster than they should based on the visible matter. Clusters of galaxies hold together with more gravity than their visible matter can provide. The patterns in the cosmic microwave background tell us there's more matter than we can account for. This invisible matter is called dark matter. It doesn't give off light. It doesn't absorb light. It doesn't reflect light. We can only detect it through its gravity, through the way it pulls on things we can see. And there's a lot of it, about 5 times more than all the normal matter combined. That means for every atom in your body, every star in the sky, every planet and comet and speck of dust, there are 5 times as much dark matter that we can't see. It's all around us, passing through us right now. It doesn't interact with normal matter except through gravity. Billions of dark matter particles might be passing through your body every second, and you can't feel them because they don't touch anything. They just sail through like ghosts. Fact 25. So when you add it all up, the universe is made of about 68% dark energy, 27% dark matter, and only 5% normal matter. That means everything you can see, everything you can touch, every star and planet and grain of sand, every atom in your body makes up less than 5% of the universe. The rest is invisible and mysterious. We live in a cosmos far stranger than we ever imagined, and we're only beginning to understand it. In that mystery, there's something beautiful. We're part of something so much bigger than ourselves, something that started with a moment of pure creation and has been unfolding ever since. That initial moment set everything in motion 13.8 billion years ago, and that motion continues today. Space is still expanding. Galaxies are still moving apart. Stars are still being born and dying. And here we are, made of matter from that first moment, made of stardust, able to think and wonder about our origins. We are beings who can contemplate the cosmos, and even though we don't understand everything, even though dark matter and dark energy remain mysterious, we've come so far in our understanding. We've traced our history back to the first seconds after creation. We've glimpsed the cosmic microwave background, that ancient light from when the universe was young. We've learned that we're connected to everything, that every atom in our bodies came from that initial moment or from the heart of a star. That's a beautiful thought to carry with you as you drift off to sleep tonight. Fact 26. The Big Bang theory wasn't always accepted by scientists. For a long time, many people believed the universe had always existed, that it had no beginning and no end. This idea was called the steady-state theory. It suggested that even though the universe is expanding, new matter constantly appears to fill the gaps, so the universe always looks roughly the same. The name Big Bang was actually given by a scientist named Fred Hoyle, who didn't believe in the theory. He said it on a radio show in 1949, trying to make the idea sound silly. But the name stuck, even though it's not really accurate. There was no bang, no explosion, no sound. Just the sudden appearance and expansion of space itself. Fact 27. Edwin Hubble was one of the first scientists to find evidence that the universe is expanding. In 1929, he was studying distant galaxies through a telescope. He noticed something strange. Almost every galaxy he looked at was moving away from us. And the farther away a galaxy was, the faster it was moving. This pattern didn't make sense if the universe was standing still, but it made perfect sense if space itself was expanding, carrying the galaxies along with it. Imagine dots on a balloon again. As you blow up the balloon, dots that are farther apart move away from each other faster than dots that are close together. Hubble's discovery was the first strong evidence that the universe had a beginning, that it started small and has been growing ever since. Fact 28. The temperature of the cosmic microwave background today is extremely cold. It measures about 2.7 degrees above absolute zero. Absolute zero is the coldest possible temperature, the point where atoms stop moving entirely. 2.7 degrees above that is incredibly cold, much colder than anything on Earth, even colder than the coldest places in Antarctica. This temperature tells us how much the universe has cooled since the Big Bang. It started at billions of degrees and has now cooled to just a few degrees above absolute zero. The expansion of space stretched out the light and carried away the heat, spreading it thinner and thinner across ever more space. The universe is growing colder as it grows older, and billions of years from now, it will be even colder still. Fact 29. Scientists use something called redshift to measure how fast galaxies are moving away from us. When something moves away from you, the light it gives off gets stretched out. The waves get longer. For visible light, longer waves look more red, so we call this redshift. It's similar to how a siren sounds different when an ambulance drives away from you. The sound waves get stretched, and the pitch drops. With light, when waves get stretched, they shift toward the red end of the spectrum. By measuring how much a galaxy's light has been redshifted, scientists can tell how fast it's moving away. And by knowing how fast it's moving and how far away it is, they can figure out how the universe has been expanding over time. Redshift is one of the most important tools we have for studying the history and structure of the cosmos. Fact 30. The universe is shaped by 4 fundamental forces. These are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity pulls things together. Electromagnetism creates light and makes magnets work and holds atoms together. The strong nuclear force holds the centers of atoms together, keeping protons and neutrons bound despite their tendency to push apart. The weak nuclear force causes certain kinds of radioactive decay and plays a role in how the sun shines. In the earliest moments after the Big Bang, these forces might have been united as one single force. As the universe expanded and cooled, they separated, like water freezing into ice with distinct crystal patterns. Understanding how these forces work and how they came to be separate is one of the great goals of physics. Fact 31. Antimatter is like a mirror version of normal matter. For every particle, there's an antiparticle with opposite properties. An electron has a negative charge, and its antimatter twin, called a positron, has a positive charge. When matter and antimatter meet, they destroy each other in a flash of pure energy. In the early universe, right after the Big Bang, there should have been equal amounts of matter and antimatter. But when matter and antimatter collide, they annihilate. So why is there anything left at all? Why didn't all the matter and antimatter destroy each other, leaving only energy? The answer is one of science's biggest puzzles. For some reason, there was slightly more matter than antimatter. For every billion antiparticles, there were 1,000,001,000 particles. When everything annihilated, that tiny extra bit of matter survived, and that leftover matter became everything we see today. Fact 32. The universe went through several distinct phases as it cooled. Each phase had different conditions and different rules. In the first tiny fraction of a second during inflation, the universe expanded faster than light. Then came a period called the quark epoch, when the universe was filled with quarks, the building blocks of protons and neutrons. Quarks couldn't form larger particles yet because it was still too hot. Then, as things cooled, quarks combined to make protons and neutrons. This was the hadron epoch. Later came the lepton epoch, dominated by lighter particles like electrons. Each phase lasted for different amounts of time and set the stage for what came next. The universe was like a construction project, with each stage building on the previous one. Fact 33. Black holes might have formed in the very early universe. These wouldn't be the black holes we know from dying stars. They would be tiny, some perhaps no bigger than an atom, but with significant mass compressed into that tiny space. Scientists call these primordial black holes. They could have formed from dense regions in the early universe that collapsed under their own gravity. Some scientists think primordial black holes might actually be what dark matter is made of, though this idea is still debated. If they exist, they would be scattered throughout the universe, invisible and nearly impossible to detect directly. They would bend space around them and pull on nearby objects with gravity, but they would give off no light. Finding them, if they're out there, is one of the challenges facing modern astronomy. Fact 34. The Big Bang brought space itself into existence. This is a strange concept to wrap your mind around. We usually think of space as just emptiness, the gap between objects. But in Einstein's theory of relativity, space is a real thing. It can bend and stretch and ripple. When massive objects move, they create waves in space itself, called gravitational waves. And in the Big Bang, space came into existence along with everything else. Before the Big Bang, there was no space for anything to exist in. The expansion didn't happen in space, it created space. Every inch of empty air, every gap between stars, every vast void between galaxies, all came from that initial moment. Fact 35. Light from the most distant galaxies has been travelling toward us for over 13 billion years. When we look at these galaxies through powerful telescopes, we're seeing them as they were in the ancient past, not as they are now. The light left them when the universe was young, less than 1 billion years old. That light has been crossing space ever since, travelling at the fastest speed possible, and it's only just now reaching our eyes. The galaxies we're seeing might not even exist anymore. They might have changed completely, merged with other galaxies, or evolved into something very different. We're looking into the past, watching ancient history unfold. In a sense, telescopes are time machines, letting us observe the universe as it was billions of years ago. Fact 36. The observable universe is about 93 billion light-years across. This might seem confusing. If the universe is only 13.8 billion years old, how can we see things that are 46.5 billion light-years away in each direction? The answer is expansion. While light was travelling toward us from distant galaxies, space itself was expanding, carrying those galaxies even farther away. So by the time the light reaches us, the galaxy that sent it is much farther away than it was when the light started its journey. The observable universe is just the part we can see, the region where light has had time to reach us. Beyond that, there's more universe, possibly infinitely more. But we can't see it because light from those distant regions hasn't had time to get here yet. Fact 37. The universe might be infinite, or it might wrap back on itself like the surface of a sphere. Scientists have tried to measure the overall shape of the universe by studying the cosmic microwave background. So far it looks flat, which suggests it might go on forever in all directions. But there's still uncertainty. If the universe does wrap around, it would be so large that we can't detect the curvature. Imagine an ant walking on a beach ball. If the ball is small, the ant would notice it's walking on a curve. But if the ball is as big as Earth, the ant would think the surface is flat. We might be like that ant, unable to detect the true shape because we can only see a small portion of the whole. Fact 38. Cosmic inflation solved several puzzles about the universe. Before inflation was proposed, scientists noticed some strange things. The universe looked the same in all directions, even though different regions were too far apart to have ever influenced each other. How did they all end up looking so similar? Inflation explained this by suggesting that all the regions we see came from one tiny patch that expanded incredibly fast. That's why they're similar. They all came from the same place. Inflation also explained why the universe looks flat and why we don't see certain exotic particles that should have been created in the Big Bang. The rapid expansion spread everything out so much that the rare particles became incredibly rare, and the curvature became undetectable. Fact 39. Quantum mechanics might have played a crucial role in the Big Bang. Quantum mechanics is the science of the very small, the rules that govern atoms and particles. At the tinier scales, things don't follow the normal rules we're used to. Particles can be in multiple places at once. They can pop in and out of existence. They can be connected across vast distances. In the first moments after the Big Bang, the entire universe was smaller than an atom, so quantum rules applied to everything. Those tiny quantum fluctuations, random variations in energy and density, might have been stretched out by inflation to become the large-scale structures we see today. The galaxies, the clusters, the cosmic web of matter, all of it might have started as quantum uncertainty, blown up to cosmic size. Fact 40. The cosmic microwave background isn't perfectly smooth. It has tiny variations in temperature, and these variations create a pattern across the sky. Scientists have mapped this pattern in incredible detail, using satellites like WMAP and Planck. The pattern tells us about the conditions in the early universe. It shows us where matter was slightly denser and where it was slightly thinner. It reveals sound waves that travelled through the plasma before recombination, frozen in place when the universe became transparent. By studying this pattern, scientists can measure the age of the universe, the amount of dark matter and dark energy, and many other important properties. The cosmic microwave background is like a fossil, preserving information about the universe's infancy. Fact 41. Sound waves existed in the early universe, rippling through the plasma like waves on a pond. Before recombination, the universe was filled with a hot plasma of protons, electrons, and photons all interacting with each other. Dense regions had more gravity, which pulled matter inward, but the pressure of the photons pushed outward. This created oscillations, regions of plasma compressing and expanding in a regular pattern. These were sound waves, though not the kind you could hear. They travelled through the plasma at about half the speed of light. When recombination happened and the universe became transparent, these sound waves froze in place. The pattern they created is visible in the cosmic microwave background, and by measuring it, scientists can learn about the composition and history of the early universe. Fact 42. The Big Bang resulted in a universe with no centre and no edge. This seems strange because we're used to things having boundaries. But remember, the Big Bang wasn't an explosion from a point into empty space. It was space itself coming into existence and expanding everywhere at once. Every point in the universe was part of the beginning. If the universe is infinite, then it has no edge because there's always more space beyond wherever you are. If it wraps around on itself, then it also has no edge, just like the surface of Earth has no edge. You can keep travelling in one direction and never fall off. And there's no centre, because every point sees the same thing, the universe expanding away in all directions. No location is special, we're all equally in the middle of everywhere. Fact 43. Neutrinos are strange particles that barely interact with anything. They're created in nuclear reactions, like the ones happening in the Sun or in the Big Bang. Trillions of neutrinos pass through your body every second, coming from the Sun and from cosmic rays and from the Big Bang itself. They pass through Earth like it's not even there. Neutrinos created in the Big Bang are still flying through space today. They're called the cosmic neutrino background, similar to the cosmic microwave background but made of particles instead of light. We can't detect them yet because they interact so weakly with matter, but they're out there, ghostly remnants of the universe's first seconds, filling space with an invisible sea of particles from the dawn of time. Fact 44. The concept of the Big Bang challenges our intuition about cause and effect. We're used to thinking that everything has a cause. Something happened that made everything begin. But if time itself started with the Big Bang, then there was no before for a cause to exist in. From a scientific perspective, cause and effect as we understand them require time. Some scientists try to extend physics backward beyond the Big Bang, imagining a larger structure that our universe emerged from. Maybe there was a previous universe that collapsed and then bounced back. Maybe our universe is one bubble in an eternal structure where new universes are constantly forming. These ideas are speculative, and we don't have evidence for them yet. For now, the Big Bang represents the limit of what we can observe and understand, the earliest moment we can probe with science. Fact 45. The elements created in the Big Bang were distributed evenly throughout space. Every region had the same mixture, about 3/4 hydrogen, 1/4 helium, and traces of lithium. This uniformity is important because it shows that the Big Bang happened everywhere at once, not in one location. If it had happened in one spot, we'd expect the elements to be concentrated there and thinner elsewhere. Instead, everywhere we look, the primordial element ratios are the same. The hydrogen and helium we see in distant galaxies has the same proportions as the hydrogen and helium in our own galaxy. This consistency across billions of light-years of space is powerful evidence that the Big Bang theory is correct. Fact 46. Einstein's equations of general relativity predict the Big Bang. When Einstein first developed these equations, which describe how gravity works and how space and time behave, he found something unexpected. The equations suggested that the universe should be either expanding or contracting. It couldn't stand still. Einstein didn't like this result because at the time, everyone thought the universe was eternal and unchanging. So he added a term to his equations called the cosmological constant, a kind of anti-gravity force that would keep the universe static. Later, when Hubble discovered that the universe really is expanding, Einstein called the cosmological constant his biggest blunder. Interestingly, the cosmological constant has made a comeback. It might be related to dark energy, the mysterious force making the expansion accelerate. Fact 47. The universe is homogeneous and isotropic on large scales. Homogeneous means it's the same everywhere. Isotropic means it looks the same in all directions. If you zoom out far enough, the universe looks uniform. Galaxies are distributed evenly throughout space when you average over large regions. This doesn't mean everything is identical. On small scales, there are planets, stars, galaxies, clusters, and voids. But when you look at scales of hundreds of millions of light years, the wrinkles smooth out. This uniformity tells us that the laws of physics are the same everywhere, that no location in the universe is special. It's called the cosmological principle, and it's a fundamental assumption in our models of how the universe works. Fact 48. The Planck epoch is the name for the earliest period after the Big Bang. From time 0 to about 10 to the negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. This is the Planck time, the smallest unit of time that has meaning in physics. During the Planck epoch, the universe was so hot and dense that our current theories of physics break down. Quantum mechanics and general relativity, the two great theories of modern physics, give contradictory results when we try to apply them to this era. We need a theory of quantum gravity, a way to describe gravity using quantum rules, to understand what happened. Scientists have proposals like string theory and loop quantum gravity, but we don't have a complete tested theory yet. Fact 49. In the beginning, equal amounts of matter and radiation existed. Radiation, meaning photons and other massless particles, just dominated the early universe. There were so many photons that their energy outweighed the mass of all the matter. This was the radiation-dominated era. As the universe expanded, the radiation cooled and thinned out. Eventually, matter became more important. This transition happened about 50,000 years after the Big Bang. From that point on, matter's gravity shaped the evolution of the universe, pulling gas together to form structures. Today, matter dominates over radiation, though dark energy now dominates over everything. Each era in cosmic history is defined by what's most important at the time, and the universe has passed through several such transitions. Fact 50. One of the most profound implications of the Big Bang is that the universe has a history. It wasn't always the way it is now. It used to be simpler, hotter, denser, younger, and it will continue to change in the future. Stars will keep forming and dying, galaxies will merge, the universe will keep expanding, growing colder and emptier. Eventually, in trillions of years, the last stars will burn out. The universe will become a dark, cold place. But that's far in the future. Right now, we live in an era when stars shine, when galaxies dance together, when planets harbor life. We're here in a special time, able to look out and see the story written in the light of distant galaxies and in the faint glow of the cosmic microwave background. We're privileged to exist in a universe that's old enough to have created the elements we're made of, but young enough to still be beautiful and bright. Fact 51. The Big Bang brought space-time into existence as a single unified thing, not as separate entities. And we usually think of space as the three dimensions we can move through, up and down, left and right, forward and backward. And we think of time as something different, something that just flows forward. But Einstein showed us that space and time are woven together into one fabric called space-time. Events don't just happen at a location, They happen at a specific place and a specific moment. The Big Bang didn't create space and then start time running. Both came into being together as inseparable partners. This four-dimensional space-time is the stage where everything in the universe plays out. Massive objects like stars and planets bend this fabric, creating what we experience as gravity. The Big Bang set this whole stage into existence, complete with all its dimensions at once. Fact 52. During the first second after the Big Bang, the universe went through more changes than it has in the billions of years since. That first second saw the formation of fundamental particles, the separation of forces, the transformation of energy into matter, and multiple phase transitions as the universe cooled. Imagine condensing all of human history into a single heartbeat. That gives you some sense of how much happened in that brief moment. After that first second, things slowed down considerably. The universe spent hundreds of thousands of years just cooling and expanding before atoms could form. Then it spent hundreds of millions of years in darkness before the first stars ignited. Compared to that explosive first second, the rest of cosmic history has been relatively calm and gradual. Yet everything that came later, every structure and complexity, was built on the foundation laid in those first moments. Fact 53. The horizon problem was one of the mysteries that led scientists to propose cosmic inflation. When we look at the cosmic microwave background, we see that the temperature is almost exactly the same in all directions. The difference from one region to another is less than 1 part in 100,000. But here's the puzzle. Regions on opposite sides of the sky are so far apart that light couldn't have traveled between them in the time since the Big Bang. They couldn't have communicated with each other, couldn't have exchanged heat, couldn't have reached the same temperature through normal processes. So how did they end up looking so similar? Inflation solved this by proposing that all the regions we can see came from a tiny patch that was in thermal equilibrium, all at the same temperature. Then inflation expanded this tiny uniform patch to enormous size, much larger than the observable universe. The regions we see on opposite sides of the sky were once close neighbors before inflation pushed them far apart. Fact 54. The universe creates particle pairs constantly, even in empty space. This happens because of quantum mechanics. According to quantum theory, you can never have truly empty space. The vacuum is full of quantum fluctuations, pairs of particles and antiparticles, popping into existence for brief moments before annihilating each other again. These are called virtual particles. They exist for such a short time that they don't violate the law of energy conservation. You can think of them as borrowing energy from the universe and paying it back almost instantly. Usually, these virtual particles don't matter much because they disappear so quickly. But in the early universe, some of these quantum fluctuations got caught up in the inflationary expansion. They were stretched out before they could disappear, becoming real particles that lasted. These quantum jitters, amplified by inflation, became the seeds of galaxies. The largest structures in the universe today started as tiny quantum fluctuations in the fabric of space-time. Fact 55. Photons, the particles of light, have been streaming through the universe since recombination. Every photon in the cosmic microwave background has been traveling for over 13 billion years without hitting anything. Think about that journey. A photon is released when an electron and proton combine to form a hydrogen atom. It flies off into space, traveling at the speed of light. It crosses vast distances, passing through voids and around galaxy clusters. Its path bent slightly by gravity but never stopped. Billions of years pass. Galaxies form and evolve. Stars are born and die. And still this photon travels, its wavelength gradually stretching as space expands. Finally, after more than 13 billion years, it enters a telescope on Earth and gets detected by human instruments. That photon has been on a journey longer than most stars exist, carrying information from an era before anything complex existed in the universe. Fact 56. The flatness problem is another puzzle that inflation helps explain. The geometry of space can be curved in different ways, It could curve back on itself like a sphere, which we'd call positive curvature. It could curve outward like a saddle, which is negative curvature. Or it could be flat, meaning parallel lines stay parallel forever. Measurements show that our universe is very close to flat, perhaps exactly flat. But here's the puzzle. For the universe to be flat today, it had to be incredibly flat in the beginning. Even the tiniest deviation from flatness would have grown over time. If the early universe had been just slightly curved, it would be obviously curved now. The fact that it's still flat suggests it started out fantastically flat, fine-tuned to an extraordinary degree. This seems suspicious, like finding a pencil balanced perfectly on its point. Inflation explains this by stretching space so much that any initial curvature got smoothed out, the way wrinkles disappear when you blow up a balloon. Fact 57. The universe doesn't expand into anything. This is one of the hardest concepts to understand about the Big Bang. We're used to things expanding into empty space. A balloon expands into the room, a city expands into the surrounding countryside. But the universe isn't expanding into some pre-existing empty space. Space itself is what's expanding. There's nothing outside the universe for it to expand into. The idea of outside the universe doesn't make sense because space only exists inside the universe. When we say the universe is expanding, we mean that distances between galaxies are increasing because the space between them is growing. It's not that galaxies are flying through space away from each other. It's that space itself is stretching, carrying the galaxies along. This distinction seems subtle, but it's important. The expansion isn't happening in space. It's happening to space. Fact 58. Baryonic matter is the term scientists use for normal matter, the kind made of protons, neutrons, and electrons. Everything you can touch, see, or detect directly is baryonic matter. Despite the name, this includes electrons even though they're technically leptons, not baryons. The term has stuck anyway. Baryonic matter makes up only about 5% of the universe's total energy content, but it's the kind of matter we understand best. It forms atoms, molecules, planets, stars, and living things. It interacts with light so we can see it. The other 95% of the universe is dark matter and dark energy, which don't interact with light and remain mysterious. But that small fraction of baryonic matter is what we're made of. It's what builds the complexity we see around us. From crystals to galaxies to consciousness, in a universe dominated by invisible components, we're made of the rare stuff that shines. Fact 59. The Big Bang set matter and energy in motion, and that motion led to the rotation we see in galaxies today. When the universe began expanding, different regions acquired different motions. These motions led to the rotation we observe in galaxies. Most galaxies spin, rotating around their centers like enormous pinwheels. This rotation came from the initial conditions and was shaped by gravitational interactions over billions of years. Small variations in density and motion in the early universe got amplified over time. As gas clouds collapsed to form galaxies, conservation of angular momentum made them spin faster, the same way an ice skater spins faster when they pull their arms in. The beautiful spiral arms of galaxies, the orderly rotation of stars around galactic centers, all trace back to tinier symmetries in the primordial universe. Fact 60. The temperature history of the universe follows a predictable pattern. At the moment of the Big Bang, temperatures were essentially infinite. Within the first fraction of a second, they had dropped to around 10 trillion degrees as the universe expanded and cooled. After 3 minutes, when nucleosynthesis happened, the temperature was about 1 billion degrees, comparable to the core of the hottest stars. By the time of recombination, 380,000 years later, it had cooled to about 3,000 degrees, similar to the surface of a red star. Today, the temperature of the universe as measured by the cosmic microwave background is about 2.7 degrees above absolute zero. This cooling will continue forever. In the far future, the temperature will approach absolute zero, and the universe will become a cold, dark place with occasional islands of warmth around any remaining stars or other energy sources. Fact 61. Gravitational waves from the Big Bang might still be detectable. Just as light from recombination survives as the cosmic microwave background, gravitational waves from even earlier times might form a gravitational wave background. These would be ripples in space-time itself, created by violent processes in the first moments, possibly during inflation. Unlike light, gravitational waves can pass through anything without being absorbed or scattered. They've been traveling freely through space since the earliest moments, potentially carrying information from times before recombination, from eras we can't see with light. Scientists are working on detectors sensitive enough to find this background of primordial gravitational waves. If we can detect them, we'll have a new window into the first fraction of a second, a way to study conditions that existed before atoms, before nuclei, before even protons and neutrons. Fact 62. The cosmological constant was Einstein's attempt to keep the universe static, but it ended up being remarkably prescient. When he realized the universe was actually expanding, he removed it from his equations, supposedly calling it his biggest mistake. But decades later, when astronomers discovered that the expansion is accelerating, scientists brought back the cosmological constant as a possible explanation for dark energy. It represents a constant energy density filling all of space. As space expands, more space gets created and more dark energy comes with it. This causes the expansion to accelerate. The cosmological constant might be related to the energy of the vacuum itself, the energy of empty space. Quantum mechanics suggests that even empty space has energy, from virtual particles constantly appearing and disappearing. However, when physicists calculate how much vacuum energy there should be, they get a number that's enormously larger than what we observe. This mismatch is called the cosmological constant problem, and it's one of the biggest unsolved puzzles in physics. Fact 63. The observable universe contains about 2 trillion galaxies, each with millions or billions or even trillions of stars. Every single one of those stars, every planet orbiting them, every atom of gas between them, emerged from the Big Bang. The sheer number is almost impossible to grasp. If you tried to count all the stars in the observable universe, counting one per second without stopping, it would take you trillions upon trillions of years, far longer than the current age of the universe. And that's just the observable universe, the part we can see. If the universe is infinite or even just much larger than the observable portion, then the total number of stars is truly beyond comprehension. All of this richness and complexity emerged from a beginning that was remarkably simple. Just energy and the laws of physics, expanding and cooling and gradually organizing itself into ever more intricate patterns. Fact 64. The concept of nothing is slippery in physics. When we say the universe came from nothing, we have to be careful about what we mean. In everyday language, nothing means the absence of everything. But in quantum physics, even empty space is something. It has properties. It can fluctuate. Virtual particles can appear in it. Others propose that the laws of nature themselves were brought into existence with the universe, that both came from the creative power of God. Still others suggest that the laws in the universe came into being together, that asking what came before is like asking what's north of the North Pole. These are deep philosophical and scientific questions that sit at the boundary of what we can currently understand or test with experiments. Fact 65. The abundance of deuterium in the universe is a sensitive test of Big Bang theory. Deuterium is a heavy form of hydrogen. Normal hydrogen has 1 proton in its nucleus. Deuterium has 1 proton and 1 neutron. It forms during Big Bang nucleosynthesis, but it's fragile. Stars destroy deuterium when it falls into them because stellar temperatures are high enough to break it apart. So all the deuterium we see today was made in the Big Bang and has survived since then without being processed through stars. The amount of deuterium we observe matches the predictions from Big Bang nucleosynthesis extremely well. This match depends on the density of normal matter in the universe. By measuring deuterium abundance, scientists can determine how much baryonic matter exists, and the answer they get agrees with measurements from the cosmic microwave background and from galaxy surveys. These independent confirmations strengthen our confidence that the Big Bang theory accurately describes the early universe. Fact 66. The universe became transparent not all at once, but over a period called the recombination epoch. This transition took about 100,000 years. Different regions became transparent at slightly different times depending on their density and temperature. As electrons and protons combined to form neutral hydrogen, photons stopped scattering off free electrons. The last scattering surface is the name we give to the boundary between the opaque plasma and the transparent gas. When we look at the cosmic microwave background, we're seeing the surface of last scattering, the place where photons last bounced off matter before traveling freely through space. This surface isn't a physical barrier, it's more like a horizon, a boundary in time rather than space. Every observer in the universe sees their own surface of last scattering, and it's always the same distance away in time, about 13.8 billion years ago. Fact 67. Galaxies formed from the bottom up, with small structures forming first and then merging to create larger ones. After the cosmic dark ages ended and the first stars ignited, they began to gather into groups. These groups merged to form dwarf galaxies. Dwarf galaxies merged to form larger galaxies, and large galaxies continued to merge, creating the giant galaxies we see today. This hierarchical structure formation is driven by gravity. Dark matter played a crucial role because it clumped together first, forming gravitational wells that attracted normal matter. The first stars formed in the densest concentrations of dark matter. Over billions of years, through countless mergers and interactions, the cosmic web of galaxies took shape. Our own Milky Way galaxy formed from many smaller galaxies merging together over billions of years, and it's still growing today as it absorbs smaller satellite galaxies, and will eventually merge with the Andromeda Galaxy. Fact 68. The physics of the Big Bang can be tested in particle accelerators here on Earth. When we smash particles together at high energies, we recreate conditions similar to those in the early universe. The Large Hadron Collider, the most powerful particle accelerator ever built, can achieve energies comparable to a trillionth of a second after the Big Bang. By studying what happens in these collisions, scientists can test their theories about particle physics and the forces that operated in the early universe. This is one of the beautiful things about physics. The same laws that governed the universe billions of years ago still apply today. We can bring a tiny piece of those early conditions into our laboratories and study them directly. Every collision in a particle accelerator is like a miniature echo of that first moment, allowing us to probe the fundamental nature of matter and energy. Fact 69. The entropy of the universe has been increasing since the Big Bang. Entropy is a measure of disorder or randomness. The second law of thermodynamics says that entropy always increases over time in a closed system. But here's something interesting. The early universe was in some ways very orderly. Everything was smooth and uniform with only tiny variations. As time passed, those small variations grew into the complex structures we see today. Stars formed, planets coalesced, life emerged. This seems like increasing order, not disorder. But from a thermodynamic perspective, the formation of stars and galaxies actually increases the total entropy. When matter clumps together under gravity, it releases energy as heat and light. This energy spreads out into space, increasing the overall disorder of the universe even as local pockets become more organized. The universe as a whole is winding down, heading toward maximum entropy, a state of complete disorder where no useful work can be done. But we're still far from that end state, living in an era where there's plenty of free energy available to drive interesting processes like star formation and life. Fact 70. The Big Bang theory makes predictions that have been confirmed repeatedly. It predicted the cosmic microwave background before it was discovered. It predicted the abundances of light elements before they were accurately measured. It predicted the expansion of the universe, which was later observed. It predicted that distant galaxies should look younger and different from nearby ones, which is exactly what we see. Every major prediction of the Big Bang Theory has been confirmed by observations. This doesn't mean the theory is complete or that we understand everything. There are still mysteries like dark matter and dark energy. There are still gaps in our knowledge about the earliest moments. But the core framework, the idea that the universe began in a hot, dense state and has been expanding and cooling ever since, is supported by overwhelming evidence from multiple independent sources. Fact 71. The universe is older than any object within it. This seems obvious, but it's worth reflecting on. The oldest stars we've found are about 13 billion years old, formed just a few 100 million years after the Big Bang. No star can be older than the universe itself. But we can use the age of old stars to check our calculations about the age of the universe. If we found a star that appeared to be 15 billion years old, that would be a serious problem for the Big Bang Theory. The fact that the oldest stars are younger than the universe's calculated age is reassuring. It means our models are internally consistent. The universe had time to expand, cool, form the first stars, and have those stars age to their current state. Everything fits together in a coherent timeline that stretches from the first moment to the present day. Fact 72. Helium is more abundant than it should be if stars were the only source. When astronomers first measured the amount of helium in the universe, they found that about 25% of all normal matter is helium. Stars produce helium by fusing hydrogen in their cores, and over billions of years they've converted a lot of hydrogen into helium. But calculations showed that stars alone couldn't have produced all the helium we observe. There simply hasn't been enough time, and not enough hydrogen has been processed through stars. This excess helium was a mystery until the Big Bang Theory explained it. If the universe started hot and dense, fusion would have happened throughout all of space during the first few minutes, producing vast quantities of helium before any stars existed. The amount predicted by Big Bang nucleosynthesis matched the observations perfectly. This was one of the key pieces of evidence that convinced scientists the Big Bang Theory was correct. Fact 73. The anthropic principle raises interesting questions about why the universe has the properties it does. Some of the fundamental constants of nature, like the strength of gravity or the mass of electrons, seem fine-tuned to allow life to exist. If they were even slightly different, stars couldn't form, or atoms couldn't exist, or chemistry would work completely differently. Why does the universe appear to be set up in a way that permits complexity and life? One answer is the anthropic principle, which says we observe a universe capable of supporting life, because if it weren't, we wouldn't be here to observe it. This is sometimes called observer selection bias. If there are many different regions with different properties, we necessarily find ourselves in one of the rare ones that allows observers to exist. This doesn't explain why our universe has the properties it does, but it does explain why we shouldn't be surprised to find ourselves in a life-friendly universe. Some scientists find this satisfying, while others see it as avoiding a deeper explanation. Fact 74. The cosmic microwave background has been measured with extraordinary precision by several satellite missions. The Cosmic Background Explorer satellite in the early 1990s confirmed that the spectrum of the CMB matches a perfect blackbody, exactly as predicted. The Wilkinson Microwave Anisotropy probe created detailed maps of temperature variations across the sky. The Planck satellite refined these measurements even further, detecting variations of a few millionths of a degree. From these incredibly precise measurements, scientists have extracted an enormous amount of information. They've determined the age of the universe, the amounts of dark matter and dark energy, the rate of expansion, the geometry of space, and dozens of other parameters that describe the cosmos. The cosmic microwave background is like a treasure trove of data, and every time we measure it more carefully, we learn something new about the universe's structure and history. Fact 75. The Big Bang happened everywhere at once, not at a single point. This is worth repeating because it's so commonly misunderstood. If you try to trace the expansion backward in time, you don't end up with all the matter converging on one location in space. You end up with all of space shrinking down to a point. Every location in the universe today was part of that initial moment. There's no place you can point to and say, the Big Bang happened there. It happened here, where you're sitting right now. It happened in every galaxy we can see. It happened everywhere simultaneously because at that moment, everywhere was the same place. Space itself has expanded since then, carrying matter along with it. But there's no center to the expansion, no special location where it all started. This is a profound shift in how we think about cosmic origins, moving from the idea of an explosion in space to the idea of space itself coming into existence and expanding. Fact 76. The universe is filled with structure on every scale you can imagine, from the smallest particles to the largest superclusters of galaxies, and all of this structure emerged from the Big Bang. On the smallest scale, we have quarks and electrons, the fundamental building blocks of matter. These combine to form protons and neutrons, which combine to form atomic nuclei. Add electrons and you get atoms. Atoms link together to create molecules. Molecules can build everything from grains of dust to planets to living organisms. On larger scales, gravity pulls matter together into stars. Stars group into galaxies. Galaxies gather into clusters. Clusters form superclusters. And superclusters arrange themselves into vast filaments and walls surrounding empty voids, creating what astronomers call the cosmic web. This entire hierarchy of structure, from the quantum scale to the cosmic scale, all traces back to tiny fluctuations in the density of matter in the early universe. Those microscopic ripples, barely 1 part in 100,000, grew over billions of years into the rich tapestry of structure we observe today. It's remarkable that such a simple beginning, just energy and space expanding uniformly with tiny variations, could lead to such incredible complexity. Fact 77. The speed of light plays a fundamental role in limiting what we can observe about the universe. Light travels at about 300,000 kilometers per second, which sounds incredibly fast. In 1 second, light can circle Earth more than 7 times. But the universe is so vast that even light takes billions of years to cross cosmic distances. The observable universe is defined by how far light could have traveled since the Big Bang. Beyond a certain distance, light hasn't had enough time to reach us yet. This creates a kind of horizon, a boundary to what we can see. As time passes, this horizon expands and we can see farther into space. But because the universe is also expanding, some regions are moving away from us faster than light can catch up. Light from those regions will never reach us, no matter how long we wait. This means there are parts of the universe we will never be able to observe, events we will never be able to witness, galaxies we will never be able to study. The universe beyond our cosmic horizon remains forever mysterious, hidden not by distance alone, but by the combination of distance and the expansion of space itself. Fact 78. Magnetic fields existed in the early universe, and may have played a role in shaping cosmic structure. Scientists aren't entirely sure how these magnetic fields originated. They might have been created during phase transitions in the very early universe, when fundamental forces separated from each other. Or they might have been generated by the first stars and galaxies and then spread throughout space. Regardless of their origin, magnetic fields pervade the universe today. They exist in galaxies, in the space between galaxies, and possibly even in the vast voids. These fields are incredibly weak compared to the magnets you might have on your refrigerator, sometimes billions of times weaker. But spread across such enormous volumes of space, they contain significant amounts of energy. Magnetic fields can influence how gas moves and how stars form. They can accelerate particles to enormous energies, creating cosmic rays that zip through space at nearly the speed of a light. They might even have affected the formation of the first structures after the Big Bang, adding another layer of complexity to the cosmic web that emerged from the simple initial conditions. Fact 79. The vacuum of space is not truly empty, even in regions far from any matter or energy sources. Quantum field theory tells us that every point in space is filled with quantum fields, invisible entities that can vibrate and create particles. These fields exist everywhere, even in the darkest void between galaxy clusters. When a field vibrates in just the right way, a particle appears. The electromagnetic field creates photons, the electron field creates electrons, and so on for every type of particle. These fields can never be turned off or removed. They're woven into the fabric of reality itself. Even in regions we might think of as completely empty, these quantum fields are present, occasionally producing virtual particle pairs that briefly exist before annihilating. This means that truly empty space is impossible. There's always something happening at the quantum level, always a background of activity that we can't directly observe but that has measurable effects. In the early universe, these quantum fields were violently active, with particles being created and destroyed in vast numbers as the universe cooled and transitioned through different phases. Fact 80. Black holes that form today are very different from the black holes that might have formed in the early universe. Modern black holes typically form when massive stars collapse at the end of their lives. They need a star to exist first, which means they couldn't form until after the first stars ignited, at least 100 million years after the Big Bang. But primordial black holes, if they exist, could have formed in the first fraction of a second. During that chaotic early period, some regions might have been dense enough to collapse directly into black holes without needing a star first. These primordial black holes could have any mass from extremely tiny, much smaller than an atom, to millions or billions of times the mass of the Sun. The smallest ones would have evaporated by now through Hawking radiation, a quantum process that makes black holes slowly lose mass over time. But larger primordial black holes could still exist today, scattered throughout the universe. They might even account for some, or all of the dark matter we detect through gravitational effects. Scientists are searching for evidence of primordial black holes by looking for their gravitational effects on light from distant stars and by studying gravitational waves from merging black holes that might be primordial in origin. Fact 81. The weakness of gravity compared to other forces is both a puzzle and a blessing. Gravity is by far the weakest of the four fundamental forces. An ordinary refrigerator magnet can overcome the gravitational pull of the entire Earth. Electromagnetic forces are about 1 trillion times stronger than gravity. Yet gravity dominates on cosmic scales because it only attracts, never repels, and it acts over infinite distances. The other forces either attract and repel or only work over short ranges. Scientists don't fully understand why gravity is so weak. This is called the hierarchy problem. Some theories propose that gravity seems weak because it's diluted across extra dimensions that we can't perceive. Or maybe there's something special about the vacuum of space that suppresses gravitational strength. Despite being weak, gravity was crucial in the evolution of the universe after the Big Bang. It pulled matter together to form stars and galaxies. If gravity had been much stronger, the universe would have collapsed back on itself long ago. If it had been much weaker, matter would never have clumped together and nothing interesting would have formed. The weakness of gravity allowed the universe to expand and cool slowly enough for complex structures to develop over billions of years. Fact 82. The cosmic web of galaxies reveals the dark matter distribution throughout the universe. When astronomers map the positions of millions of galaxies, a clear pattern emerges. Galaxies aren't scattered randomly through space. They're arranged in long filaments and sheets surrounding enormous empty regions called voids. This structure looks remarkably like a three-dimensional spiderweb stretched across the cosmos. Computer simulations of the universe's evolution show that this pattern is created primarily by dark matter. In the early universe, dark matter had slight density variations, the same tiny ripples that we see in the cosmic microwave background. Over billions of years, gravity amplified these variations. Dense regions attracted more matter and became denser. Sparse regions lost matter and became emptier. Dark matter, being 5 times more abundant than normal matter, dominated this process. It formed the scaffolding first, creating gravitational wells where normal matter could collect. Gas flowed along the dark matter filaments, eventually forming galaxies where the filaments intersected, or where they were densest. By studying the cosmic web, we're really studying the distribution of invisible dark matter that shaped the visible universe. Fact 83. Time itself behaves differently in the presence of strong gravity, a consequence of Einstein's relativity that connects directly to the Big Bang. Near massive objects, time runs slower than it does far away in empty space. This has been tested and confirmed countless times. Atomic clocks at different altitudes tick at slightly different rates. Satellites have to account for time dilation, or their navigation systems wouldn't work. In extreme cases like near a black hole, time dilation becomes dramatic. An observer falling toward a black hole would experience time normally, but to someone watching from far away, the falling observer would appear to slow down and freeze at the event horizon. In the early universe, when everything was compressed into a tiny space, time behaved in ways that are hard to comprehend. The extreme densities and temperatures meant that space-time was curved intensely. As you trace time backward toward the Big Bang, things get stranger. The concept of a smooth flow of time breaks down. Quantum effects become important. Time might have had a beginning at the Big Bang, or it might connect to something else that we don't yet understand. These are questions at the frontier of theoretical physics, where our best theories give unclear or contradictory answers. Fact 84. The night sky appears dark even though the universe is filled with stars in every direction, a puzzle known as Olber's paradox. If the universe were infinite, eternal, and static, with stars distributed evenly throughout, then every line of sight should eventually hit a star. The entire sky should be as bright as the surface of the sun. But obviously the night sky is dark except for scattered points of light. The Big Bang resolves this paradox. The universe isn't infinitely old. Light from distant stars hasn't had enough time to reach us yet. Also, the expansion of space redshifts light from distant galaxies, shifting it into wavelengths we can't see with our eyes. And because the universe has a finite age, there are only a finite number of stars we can observe. The darkness of the night sky is actually evidence for a universe with a beginning, a universe that hasn't existed forever. Every time you look up at a dark sky sprinkled with stars, you're seeing evidence of the Big Bang. The darkness between the stars tells us that the universe is young and expanding. Fact 85. Energy cannot be created or destroyed according to the first law of thermodynamics, yet the Big Bang seems to bring all the energy in the universe into existence. This apparent contradiction puzzles many people. How can everything begin if energy can't be created? The answer lies in understanding what we mean by the total energy of the universe. When you account for all forms of energy, including the negative gravitational potential energy, the total energy of the universe might actually be zero. Gravity is a negative energy, in the sense that you have to add energy to separate objects that are gravitationally bound. All the positive energy in matter, light, and motion might be exactly balanced by the negative gravitational energy of all that matter attracting itself. If the total energy is zero, then the universe doesn't violate conservation of energy by coming into existence. It's like borrowing money from one account and depositing it in another. The total balance hasn't changed. This is a subtle and debated point in cosmology. Some physicists argue that energy conservation doesn't even apply to the universe as a whole because conservation laws depend on symmetries in time, and time behaves strangely in an expanding universe. But the idea that the universe might be a zero-energy state is an elegant possibility. Fact 86. Stars are the engines that transform the simple universe into a complex one. After the Big Bang, the universe contained only the lightest elements. For hundreds of millions of years there was no carbon, no oxygen, no iron, none of the elements that make up planets and life. Then the first stars ignited and everything changed. Inside their cores, hydrogen fused into helium, releasing enormous amounts of energy. In more massive stars, helium fused into carbon and oxygen. Still heavier elements formed in the cores of the largest stars. When these stars exploded as supernovas, they scattered their enriched material into space. The next generation of stars that formed from this enriched gas contained traces of heavy elements. These second-generation stars could form planets because they had solid material to build from. The process continued over billions of years, each generation of stars adding more heavy elements to the cosmic mix. The Sun is a relatively late-generation star, formed about 4.5 billion years ago from a cloud of gas that had been enriched by countless earlier generations of stars. The Earth and everything on it, including you, is made from material that cycled through multiple stars over billions of years. Stars are not just lights in the sky. They are the factories that built the periodic table, element by element, from the simple raw materials provided by the Big Bang. Fact 87. The universe will continue to expand forever according to current observations and theory. In the past, scientists wondered if the expansion might eventually stop and reverse. Maybe gravity would slow the expansion over time until everything started falling back together, culminating in a big crunch, the opposite of the Big Bang. But the discovery that the expansion is accelerating changed this picture dramatically. Not only is the universe not slowing down, it's speeding up. If this continues, and we have no reason to think it won't, the universe will expand forever, growing colder and emptier as time goes on. Eventually, trillions of years from now, the accelerating expansion will push distant galaxies beyond our cosmic horizon. They'll move away faster than light can travel, disappearing from view. In perhaps 100 trillion years, all the stars will have burned out. Black holes will be the only remaining compact objects, and even they will eventually evaporate through Hawking radiation, though this takes an almost unimaginable amount of time. The final fate of the universe appears to be a cold, dark, empty expansion continuing forever, with any remaining particles spread so thinly that they never encounter each other. This is called the heat death, or Big Freeze scenario. Fact 88. The symmetry of the laws of physics has deep connections to the Big Bang and the universe's evolution. Physicists have discovered that symmetries, situations where something remains unchanged under certain transformations, are intimately related to conservation laws. If the laws of physics are the same at all times, energy is conserved. If they're the same at all places, momentum is conserved. If they're the same, regardless of orientation, angular momentum is conserved. These symmetries seem to have been present from the beginning, built into the fabric of reality. But some symmetries appear to be broken. For example, there's more matter than antimatter, a breaking of matter-antimatter symmetry that happened in the early universe for reasons we don't fully understand. The separation of the fundamental forces as the universe cooled is another example of symmetry breaking. At very high energies, the forces might be unified with high symmetry. As energy decreases, the symmetry breaks, and the forces become distinct. Understanding these symmetries and how they break is crucial to understanding why the universe has the properties it does, why the laws of physics take the forms they do, and what happened in the earliest moments. Fact 89. Cosmic rays are high-energy particles that constantly bombard Earth from space, and some of them might date back to shortly after the Big Bang. Most cosmic rays are protons or atomic nuclei accelerated to enormous energies by supernova shockwaves or by exotic objects like pulsars and black holes. They travel through space at nearly the speed of light, and when they hit Earth's atmosphere, they create showers of secondary particles. We're being hit by these particles all the time, though they rarely cause any harm. But some cosmic rays have truly extreme energies, millions of times higher than anything we can produce in particle accelerators. Where do these ultra-high energy cosmic rays come from? We don't know for certain. They might be produced by the most violent events in the universe, like colliding black holes or the jets from supermassive black holes at galaxy centers. Or they might be exotic particles left over from the very early universe, heavy remnants from the Big Bang era that are finally decaying. When these particles hit our atmosphere, they give us a glimpse of physics at energies that existed shortly after the universe began. In a sense, they bring pieces of those early conditions to our doorstep. Fact 90. The fine structure constant is a number that appears throughout physics, describing the strength of electromagnetic interactions. Its value is approximately 1/137, and nobody knows why it has this particular value. It's a dimensionless number, meaning it's just a pure ratio without any units. You can measure it using completely different experiments in different areas of physics, and you always get the same answer. This constant affects how atoms behave, how light interacts with matter, how chemistry works. If it were slightly different, atoms would be unstable or stars wouldn't shine the way they do. Scientists have looked at light from distant galaxies, light that was emitted billions of years ago, to see if the fine structure constant has changed over cosmic time. So far, it appears to be truly constant, the same now as it was shortly after the Big Bang. But why does it have the value it does? This is one of the deep mysteries of physics. Some theories suggest it might be related to the geometry of extra dimensions or to the properties of fundamental strings if string theory is correct. For now, we can measure it precisely, but we can't explain it. It's one of the fundamental parameters that define our universe, set somehow at the beginning, or by whatever conditions gave rise to the Big Bang. Fact 91. Galaxies are not spread uniformly through space but cluster together under gravity's influence, forming groups and clusters that are themselves clustered into superclusters. Our own Milky Way galaxy is part of the local group, a collection of about 50 galaxies including the Andromeda galaxy and several smaller companions. The local group is in turn part of the Virgo supercluster, which contains thousands of galaxies spread across 50 million light-years. And the Virgo supercluster is part of an even larger structure called Laniakea, meaning immeasurable heaven in Hawaiian. A supercluster of superclusters containing about 100,000 galaxies. All of this structure traces back to the initial density fluctuations in the early universe. The cosmic microwave background shows us what those fluctuations looked like when the universe was just 380,000 years old. Computer simulations can start with those initial conditions and evolve them forward using the laws of gravity and physics. The results match remarkably well with what we observe today. The distribution of galaxies across space is not random. It's a pattern that emerged inevitably from the initial conditions, shaped by billions of years of gravitational evolution. We can read the history of the universe in the arrangement of galaxies across the sky. Fact 92. Neutrinos are among the most abundant particles in the universe, second only to photons. For every proton or neutron in the cosmos, there are about 1 billion neutrinos left over from the Big Bang. These relics are called the cosmic neutrino background, similar to the cosmic microwave background but consisting of particles rather than light. These Big Bang neutrinos have cooled along with the universe and now have extremely low energies. They're moving slowly, at least by particle physics standards, travelling at speeds far below the speed of light. They fill all of space uniformly, a vast invisible sea of particles that we're swimming through right now. About 300 billion of them pass through every square metre every second, including through your body. They interact so weakly with matter that they pass through the entire Earth as if it weren't there. Detecting them is incredibly difficult, and we haven't yet directly observed the cosmic neutrino background. But we're confident it exists because our theories of the Big Bang require it. These ghost particles carry information about the universe when it was just 1 second old, a time we can't observe with light because the universe was still opaque. If we can find a way to detect the cosmic neutrino background, it will open a new window into the earliest moments of cosmic history. Fact 93. The concept of a multiverse has emerged from some interpretations of quantum mechanics and from theories of cosmic inflation. If inflation happened once, what's to stop it from happening again somewhere else? Some models suggest that inflation never completely ends. Instead, it stops in some regions, creating bubble universes like ours, while continuing in others. Each bubble would be a separate universe, with potentially different properties. The physical constants might be different. The laws of physics might take different forms. Most of these universes would be lifeless, unable to form stars or complex structures. But in an infinite multiverse, every possibility would be realized somewhere. We find ourselves in a universe with properties that allow life because we couldn't exist in any other kind. This is an expansion of the anthropic principle to a cosmic scale. The multiverse idea is controversial because other universes, if they exist, might be forever beyond our ability to observe or test. Science relies on making predictions and testing them against observations. How can we do science about something we can never observe? Yet the idea arises naturally from theories that seem to work well for explaining what we can observe. It's a fascinating puzzle at the boundary of physics, philosophy, and cosmology. Fact 94. The Hubble constant measures how fast the universe is expanding, but determining its exact value has proven surprisingly difficult. The constant is named after Edwin Hubble, who first measured the expansion. It tells us how fast galaxies appear to be moving away for every megaparsec of distance. A megaparsec is about 3.3 million light-years. Different methods of measuring this constant give slightly different answers, and the discrepancy has grown with more precise measurements. This is called the Hubble tension. One way to measure it uses the cosmic microwave background and our understanding of the early universe. Another way uses observations of distant supernovas and other cosmic landmarks. The two methods disagree by about 10%, which is more than can be explained by measurement errors. This might mean there's something wrong with our understanding of either the early universe or the recent universe. Or it might mean there's new physics we haven't discovered yet, perhaps related to dark energy or dark matter. Resolving the Hubble tension is one of the major goals of current cosmology. The answer might reveal something fundamental about how the universe evolved from the Big Bang to today. Fact 95. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang. They release as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. These bursts come from distant galaxies and are detected about once per day by satellites monitoring the sky. Some are caused by the collapse of massive stars into black holes. Others come from colliding neutron stars. When they occur, they briefly outshine all other sources in the universe. If a gamma-ray burst happened in our galaxy within a few thousand light-years of Earth, it could be catastrophic, stripping away the ozone layer and potentially causing mass extinctions. Fortunately, they're rare in any given galaxy, and we haven't detected any nearby threats. These violent events remind us that the universe is not a peaceful place. Even billions of years after the Big Bang, enormous energies are still being released in stellar deaths and collisions. The universe may be expanding and cooling overall, but locally there are still events approaching the energy densities of the early cosmos. Each gamma-ray burst is like a small echo of that first moment, a brief return to conditions of extreme heat and energy density. Fact 96. The search for the theory of everything aims to unite quantum mechanics and general relativity into a single framework that could describe the universe from the Big Bang to today. Quantum mechanics governs the world of the very small, explaining atoms, particles, and the fundamental forces except gravity. General relativity governs the large scale, explaining gravity, black holes, and the curvature of space-time. Both theories work incredibly well in their domains, but they're mathematically incompatible. When you try to apply quantum mechanics to situations with strong gravity, like the Big Bang singularity or the center of a black hole, you get nonsensical results, infinities that can't be removed. This suggests that we're missing something fundamental. Candidate theories like string theory and loop quantum gravity attempt to bridge this gap. They propose that at the smallest scales, smaller than anything we can currently observe, space and time have different properties than we expect. Space might be discrete rather than continuous. Time might not be fundamental, but might emerge from something deeper. If we can find the theory of everything, it will finally let us describe the first moment in a mathematically consistent way. It will answer questions about what happened at time zero and whether asking about before the Big Bang makes sense. Fact 97. The arrow of time, the fact that time seems to flow in only one direction, might be connected to the Big Bang. We remember the past, but not the future. Eggs break but don't spontaneously reassemble. Heat flows from hot to cold, but not the reverse. All of these are manifestations of the second law of thermodynamics, which says that entropy increases over time, but the fundamental laws of physics are time-symmetric. If you could watch a video of particles interacting and someone played it backward, you couldn't tell which direction was forward in time based on the physics alone. So where does the arrow of time come from? The answer might be in the initial conditions set up by the Big Bang. The early universe was in a state of very low entropy despite being hot and dense. It was highly ordered, with matter distributed almost uniformly. As the universe expanded and evolved, entropy increased. Stars formed, burned fuel and died, converting useful energy into waste heat. This process can't be reversed. The arrow of time points in the direction of increasing entropy, from the low entropy beginning toward a high entropy future. In a sense, We experience the flow of time because the universe started in such an ordered state. If it had started in maximum entropy, nothing interesting would happen, and there would be no sense of time passing. Fact 98. The density of the universe is extremely close to a critical value that determines its ultimate fate and geometry. If the density is exactly equal to the critical density, the universe is flat and will expand forever, gradually slowing but never quite stopping. If the density is higher, the universe is closed and would eventually collapse back on itself. If it's lower, the universe is open and will expand forever, accelerating more and more. Measurements show that the total density, including matter, and dark energy, is very close to critical, within 1% as far as we can measure. This precise balance seems suspicious. Why should the density be so close to this particular value? This is called the flatness problem. Inflation provides an answer. Any initial curvature would have been smoothed out by the rapid expansion during inflation, leaving the universe flat or very nearly flat. As we measure the cosmic microwave background and the distribution of galaxies with increasing precision, we continue to find that the universe is flat to within our measurement errors. This confirms a prediction of inflation and gives us information about the total amount of matter and energy in the cosmos. Fact 99. Every atom in your body has a history that stretches back to the Big Bang. The hydrogen atoms in your body, about 10% of your atoms by count, were formed in the first 3 minutes after the universe began. The heavier elements, carbon, nitrogen, oxygen, and others, were forged in stars over billions of years. Some came from stars that lived and died before the sun was born. Others might have come from supernovas that exploded just before the solar system formed, their shockwaves perhaps even triggering the collapse of the gas cloud that became our sun. The iron in your blood rode a shockwave from a dying star, travelled through space for millions or billions of years, and eventually incorporated into the proto-Earth during its formation 4.5 billion years ago. It was recycled through the planet's interior, brought to the surface by volcanoes or tectonic activity, weathered into soil, taken up by plants, eaten by animals, and eventually became part of you. Every breath you take contains atoms that were once part of stars, scattered across the galaxy, and brought together by the long cosmic processes that started with the Big Bang. You're not separate from the cosmos. You are made of it. Your atoms have been on an incredible journey, and they carry the history within them. Fact 100. The story of the Big Bang is ultimately a story of emergence and connection. It shows us how complexity arises from simplicity, how the rich, intricate universe we inhabit emerged from elementary particles and fundamental forces. In the beginning, there was only energy, and the laws of physics God set in motion. No atoms, no molecules, no stars, no life. No consciousness, just pure potential, waiting to unfold. Over 13.8 billion years, that potential has gradually realized itself. Particles combined into atoms, atoms gathered into gas clouds collapsed into stars, stars created new elements and scattered them into space. Second-generation stars formed with planets. On at least one of those planets, chemistry became complex enough to support life. Life evolved and eventually became conscious, able to look back and ask questions about its own origins. We are beings who can contemplate the cosmos. The Big Bang connects us to everything else in existence. Every person you meet is made of the same primordial hydrogen and stellar elements. Every tree, every animal, every planet in the sky shares this common origin. We are all part of the same cosmic story, branches on the same family tree that has its roots in the first moment. In understanding the Big Bang, we come to understand our place in the cosmos, our connection to the deep past and the distant future. We learn humility in recognizing how vast the universe is and how small we are within it, but we also find meaning in being part of something so grand, so ancient, so beautiful. That initial moment set everything in motion, and that motion continues today. Space is still expanding. Galaxies are still moving apart. Stars are still being born and dying. And here we are, made of matter from that first moment, made of stardust, able to think and wonder about our origins. As you drift off to sleep tonight, you carry within you the legacy of that beginning, the memory of stars, the gift of existence that began so long ago in a moment of pure creation. Rest well, traveller of the cosmos. You are home.